Hello everyone, my name is Santosh and I am a student of Chemistry Honours first year. Here is an audio video lecture. Topic name Alkanes. Introduction. The simplest organic compounds are hydrocarbons, the compounds containing only carbon and hydrogen. Depending upon the framework of carbon atoms in their molecules, the hydrocarbons may have either open chain or ring structures. In addition, they have may be saturated or unsaturated in character according to the nature of carbon-carbon bonds in them. Due to these variations, hydrocarbons have been divided into different classes. We shall discuss the various classes of hydrocarbons one by one, starting with alkanes and cycloalkanes. Structure of alkanes. Alkanes are open chain saturated hydrocarbons having the general formula CnH2n plus 2, where n is the number of carbon atoms. They contain only single covalent bonds between carbon and carbon or carbon and hydrogen in their molecules. As such, each carbon atom is bonded to four other atoms, as is clear from the formula of methane, ethane, and propane, the first three members of alkanes. The bonds in alkanes are formed by overlapping of sp3 hybridized orbitals of each carbon atom with similar orbitals of other carbon atoms or 1s orbitals of hydrogen atoms. As a result, all the four bonds linking the carbon atoms with other atoms are sigma bonds. As these bonds are quite strong and are not easily attacked by other reagents, alkanes do not react with usual laboratory reagents under ordinary conditions. That's why they are termed as saturated hydrocarbons or paraffins. It may also be noted that due to sp3 hybridization of carbon atoms of alkanes, the four bonding orbitals of each carbon are directed towards the four corners of a tetrahedron. For instance, let us consider the case of methane, the simplest alkane. In the formation of its molecule, the four sp3 orbitals of the only carbon atom overlap the 1s orbitals of the four hydrogen atoms, which are situated at the corners of tetrahedral. Represents a molecular model of methane. Simplified three-dimensional representation of the molecule. In this representation, the wedge represents the bond point towards the observer out of the plane of the paper. The hatched line represents the bond going away from the observer behind the plane of the paper, and normal lines show the bond in the plane of the paper. Each carbon hydrogen bond has a length of 110 picometer or 1.10 angstrom, and each hydrogen carbon hydrogen angle is 109 degree 28 second. Similarly, in case of ethane, figure 4.2, and higher alkanes, the relative arrangement of the bonds is always tetrahedral, although the different bond angles may be slightly different from the regular tetrahedral value of 109 degree 28 second. The carbon hydrogen bond length is about 110 picometer, while the carbon carbon bond length is 154 picometer or nearly so. On account of the tetrahedral arrangement of the four bonds formed by each carbon atom, the molecules of alkanes are 3D in nature. Moreover, in case of alkanes containing more than two carbon atoms, the carbon atoms of the chain do not actually lie along a straight line. This is quite obvious from the model of propane as shown in the figure 4.3. In fact, for higher alkanes, the carbon-carbon chains can assume a variety of zigzag shapes, but for the sake of convenience, the carbon atoms are written in a straight line so far as possible to have a planar representation as shown below. Methane, ethane, and propane. Classification of carbon atoms in alkanes. The carbon atoms present in alkanes can be divided into four categories as given below. Primary carbon atom. It is a carbon atom which is linked directly to either one or no carbon atom. Secondary carbon atom. It is carbon atom which is linked directly to two carbon atoms. Tertiary carbon atom, it is carbon atom which is linked directly to three carbon atoms, and quaternary, it is a carbon atom which is linked directly to four carbon atoms. For example, in the formula given below, there are five primary, one secondary, one tertiary, and one quaternary carbon atoms. Hydrogen atoms are also classified as primary, secondary, and tertiary accordingly as they are linked to a primary, secondary, and tertiary carbon atom respectively. Thus, in example given above, there are 15 primary hydrogens, 2 hydrogen, 2 secondary hydrogens, and 1 tertiary hydrogen. Structural isomerism in alkanes. Each of the first three members of alkanes, methane, ethane, and propane, can have only one structural formula. However, the higher members from butane onwards can be represented by more than one structural formula and thus exhibit structural isomerism. The various isomers of the same hydrocarbon differ in the framework of the chain of carbon atoms, and therefore isomerism exhibited by alkanes is termed chain isomerism. For example, butane exists in the form of two isomers as shown, N-butane and isobutane. Similarly, pentane C5H12 exists in the form of three isomers, which are N-pentane, isopentane, or neopentane. C6H14 exists in the form of five isomers. C7H16 has 9 isomers, and C8H18 has 18 isomers, and so on. Natural sources of alkanes. Petroleum, which occurs naturally below the surface of Earth, is a mixture of many hydrocarbons, most of which belong to the alkane series. Natural gas, which issues from the petroleum field, and fuel gases obtained from the coal, contain lower alkanes. The waxy constituents of some plants have also been found to contain alkanes. For example, pine wood and turpentine oil contain N-heptane, while the leaves of cabbage contain N-noncoxane, that is C29H60. General method of preparation. The preparation of alkanes by synthetic methods is only rarely carried out. The usual practice is to isolate these hydrocarbons, particularly the lower ones, from some suitable natural sources. However, some of the general methods which can be employed for their preparation are discussed as: first is the hydrogenation of unsaturated hydrocarbons, the Sabatier and Sanderson reaction. Alkenes or alkynes can react with the hydrogen in the presence of catalyst, finally divided nickel, platinum, or palladium to form alkanes. CnH2n plus H2 in the presence of nickel at 525 to 575 Kelvin gives CnH2n plus 2. Ethylene plus hydrogen in the presence of nickel gives ethane. Alkyne plus hydrogen in the presence of nickel at 525 to 575 Kelvin gives CnH2n plus 2. Acetylene plus hydrogen in the presence of nickel at 525 to 575 Kelvin gives ethane. The use of nickel as a catalyst for a hydrogenation requires a temperature of about 525 to 575 Kelvin. But if platinum or palladium is used as catalyst, the reaction can take place even at room temperature. Methane cannot be prepared by this method, as the starting alkene or alkyne must contain at least two carbon atoms. The second one is the reduction of alkyl halides. Alkyl halides can be reduced directly or through the formation of Grignard reagent to form alkanes. Direct reduction. The direct reduction of alkyl halides is generally carried out with the chemical reducing agents such as zinc and HCl, or zinc copper couple and alcohol, or with hydrogen in the presence of palladium catalyst. The reduction may also be carried out by heating the alkyl halides with hydrogen iodide in the presence of red phosphorus in a sealed tube. For example, C2H5I means ethyl iodide plus Hi in the presence of red phosphorus. gives ethane plus I2. Second method, reduction through the formation of Grignard reagents. This is an indirect method of reducing alkyl halides. A solution of an alkyl halide is dry ether is treated with magnesium to form an ethereal solution of alkyl magnesium halide, commonly known as the Grignard reagent. Rx plus Mg in the presence of dry ether gives RMgX. The Grignard reagent are easily decomposed by water producing alkanes. It may be pointed out that the alkenes and the alkyl halides used for the preparation of alkanes by the above mentioned methods are themselves generally obtained from alcohols. But the alcohols cannot be directly converted into alkanes as the hydroxy groups of most alcohols resist reduction to corresponding alkanes. Third method for the preparation of alkanes is Wood's reaction. This reaction brings about the union of two alkyl radicals by the action of metallic sodium upon alkyl halides in dry ether. The resultant products are alkanes with a carbon skeleton having higher number of carbon atoms than the reacting alkyl halides. Rx alkyl halide plus 2Na plus Xr in the presence of dry ether gives alkane RR plus 2NaI. It may be noted that when the reaction involves two molecules of the same alkyl halide, a symmetrical alkane having an even number of carbon atoms is formed. For preparing an unsymmetrical alkane containing 3 or more than 3 carbon atoms, for example propane, a mixture of different alkyl halides has to be used. CH3Br plus 2Na plus Br CH2CH3 in the presence of dry ether gives propane plus 2Na But the products obtained by using different alkyl halides consist of mixtures of alkanes which cannot be easily separated. This is because the two alkyl halides also react separately with sodium to form two more hydrocarbons as products of the side reactions. Thus, in case of the above reaction, ethane and butane are also obtained. The main feature of Wood's reaction is that it leads to the formation of a carbon-carbon bond. As such, the reaction can be employed for preparing compounds containing higher number of carbon atoms from those containing lesser number of carbon atoms. For example, ethane may be obtained from methane as CH4 plus Cl2 give rise to CH3Cl plus HCl, CH3Cl plus 2Na plus CH3Cl give rise to CH3CH3 plus 2NaCl. The order of reactivity of different alkyl halides in this reaction is iodides, then bromides, then chlorides. Limitation of Wood's reaction. It is suitable only for the preparation of symmetrical alkanes. It cannot be used for the preparation of methane, and tertiary alkyl halides cannot be used in this reaction. Fourth one is the Corey-House synthesis. This method was developed around 1970 and is a much better method than Wood's reaction for preparing alkanes containing higher number of carbon atoms than the reactants taken. It consists of reaction between an alkyl halide and a lithium dialkyl copper. R-X plus R2CuLi give rise to R plus RCu plus LiX. Means alkyl halide plus lithium dialkyl copper give rise to alkane plus RCu plus LiX. For example, N-butyl bromide plus lithium dimethyl copper give rise to N-pentane plus methyl copper plus lithium bromide. Lithium dialkyl copper required in the reaction is itself prepared from the alkyl halide as illustrated below. Rx plus 2Li in the presence of dry ether give rise to RLi plus LiX. 2RLi plus CuX give rise to R2CuLi plus LiX. To obtain good yield of alkanes, alkyl halide used is generally a primary alkyl halide, while the alkyl group in lithium dialkyl copper may be primary, secondary or tertiary. An important feature of this reaction is that it can be used for preparing all types of alkanes, whether symmetrical or unsymmetrical, whether straight chain or branch chain. The next one is Kolbe's electrolytic reaction. In this reaction, concentrated aqueous solution of sodium or potassium salts of monocarboxylic acid is subjected to electrolysis to get alkanes. 2RCOONA plus 2H2 on electrolysis gives RR alkane plus 2NaOH plus H2. And the reaction takes place as 2RCOONA on ionization gives 2RCOO negative plus 2Na positive. 2RCOO negative minus 2 electron give rise to 2RCOO give rise to RR plus 2 CO2 at anode, and 2H positive plus 2 electrons give rise to H2 at a cathode. The discharge potential of hydrogen ions is lower than that of the sodium ions. Therefore, H positive ions are discharged at the cathode, liberating H2, while Na positive ions remains in solution. For example, 2CH3CONA, the sodium ethanoate or the sodium acetate on equilibrium gives rise to CH3CO negative plus 2Na positive. 2CH3CO negative, 2 electrons give rise to 2CH3CO give rise to CH3CH3 plus 2CO2 at anode, and 2H positive plus 2 electrons give rise to H2 at cathode. This is a good method for the preparing ethane and higher alkanes having even number of carbon atoms. Methane cannot be prepared by this method. The sixth one is the decarboxylation of monocarboxylic acids. When heated with soda lime, that is NaOH plus CaO, sodium salts of monocarboxylic or fatty acids undergo decarboxylation to form alkanes. The reaction involves the elimination of carbon dioxide from carboxylic group. Active component of soda lime in this reaction is NaOH, but it is not employed such because it melts on heating and is deliquescent as well. RCONA plus NaOH in the presence of CaO gives rise to RH, that is alkane plus Na2CO3. Oakwood and co-workers in 1950 have shown that the reaction proceeds according to the above equation only in the case of sodium acetate. In case of higher members, various side products are also obtained. Thus, in the case of sodium propionate, the reaction gives methane, hydrogen, and certain unsaturated hydrocarbons also in addition to ethane. And the reaction is CH3CONA plus NaOH give rise to CH4 plus Na2CO3. Preparation of methane. Besides method number 2, 4 and 6 described above, methane can also be prepared conventionally by dropping water over aluminium carbide. Al4C3 plus 12H2O give rise to 4AlOH thrice plus 3CH4. The gas obtained by this method is generally contaminated with hydrogen and acetylene. Preparation of ethane. Although ethane can be prepared by any of the general methods of preparation, it is generally prepared in the laboratory by the reduction of ethyl iodide or ethyl bromide with nascent hydrogen produced by the action of zinc copper couple on ethyl alcohol. 2C2H5OH plus Zn in the presence of copper give rise to C2H5O twice Zn plus 2H. CH3CH2I plus 2H give rise to CH3CH3 plus HI. Physical properties of alkanes. Physical state. The lower member of alkanes containing up to 4 carbon atoms are colorless gases. The higher normal alkanes having 5 to 17 carbon atoms are colorless liquids, and beyond that they are colorless solids at room temperature. Boiling point. The boiling point of N alkanes increase regularly with the increasing number of carbon atoms. There is an increase of about 20 to 30 degree for each carbon atom added to the chain, except in the first few cases where the increase is much more. This can be explained in the term of intermolecular forces of attraction. Alkanes are non-polar compounds having weak van der Waals forces of attraction between their molecules. These forces act along the surface of molecules and their magnitude increases with increase in the surface area. As the molecular size of alkanes increases, the surface area and the strength of van der Waals forces also increase. As a result, the boiling point also increase. Amongst the isomeric alkanes, there are small differences in the boiling points of various isomers. The branch chain isomers have invariable lesser boiling point than the normal compounds, and the greater the branching, the lower is the boiling point of the branched isomer. For instance, the boiling points of N-pentane, isopentane and neopentane are 309, 301 and 282.5 Kelvin respectively. As we can see, they are decreasing on increasing the branch. This is due to the fact that branched isomers are more compact. They have lesser surface area than their normal counterparts. Due to lesser surface area of such molecules, the van der Waals forces of attraction operating between them are comparatively weaker. As such, lesser energy is needed to overcome these forces for the boiling to take place, and therefore their boiling points are lower. Melting point. The melting points of alkanes do not show a very smooth gradation with the increase in molecular size. For instance, let us consider the melting points of N-propane to N-octane. Propane का 85.9, propane butane 138, pentane 143.3, hexane 179, heptane 182.5 and octane 216.2. It may be seen that increase in the melting point is much more in moving from an alkane having odd number of carbon atoms to the higher alkanes than in moving from an alkane having even number of carbon atoms to the higher alkanes. This is essential because the intermolecular forces in a crystal depends not only upon the size of the molecule but also upon how well the molecules fit into the crystal lattice. It has already made clear that the carbon in alkanes forms zigzag type of chain rather than a straight chain. Now in N-alkanes containing an even number of carbon atoms, the terminal methyl groups lie on the opposite side of the zigzag chain. On the other hand, in case of N-alkanes having odd number of carbon atoms, the terminal methyl groups lie on the same side of the chain as given below. It appears that the alkanes having an odd number of carbon atoms do not fit in so closely together in the crystal structures as the alkane having an even number of carbon atoms. As a result, the energy required to break the crystal structure and thus melts the alkanes is lesser in case of the alkanes having odd number of carbon atoms. That's why they have lesser than expected melting points as shown by only a slight increase in melting point in moving from an even number alkane to the higher odd number alkane. Specific gravity. The specific gravities of the alkanes also increase with increasing molecular weights but become constant at about 0.8. This implies that all the alkanes are lighter than water. Solubility. Due to nearly same electronegativity of carbon and hydrogen atoms present in them and the symmetrical shape of their molecules, alkanes are non-polar in character. As such, they are insoluble in polar solvents such as water but dissolve freely in polar solvents such as ether. The solubility decreases with the increase in the molecular weight. Chemical properties. The molecular structure of alkanes involves only carbon-carbon and carbon-hydrogen single bonds. As all these bonds are sigma bonds and are practically non-polar in nature, alkanes constitute a rather unreactive class of compounds. They are quite inert towards the common reagents such as acids, alkalis, and oxidizing or reducing agents under ordinary conditions. However, under strong conditions, alkanes do not undergo a few reactions, mostly involving substitutions. The reactions generally take place by free radical and chain mechanism. The important reaction of alkanes are described as: the first one is the halogenation. This reaction involves the replacement of one or more hydrogen atom of an alkane by a corresponding number of halogen atoms. Chlorination and bromination are carried out by the treating the alkane with chlorine or bromine in the presence of light or at high temperature. For example, when chlorine reacts with methane undergo these conditions, all the four hydrogen atoms of methane can be successively replaced by chlorine. Bromination, though similar to chlorination, takes place readily. Iodination of alkanes is extremely slow and reversible, that is CH4 plus I2 give rise to CH3I methyl iodide plus HI in a reversible process. Therefore, direct iodination of alkanes cannot be brought out. However, the reaction may be carried out in the presence of an oxidizing agent such as iodic acid, nitric acid, etc., which converts the hydroiodic acid produced into iodine, that is 5Hi plus HiO3 give rise to 3I2 plus 3H2O. Fluorination. Fluorination of alkanes is not generally carried out because it takes place with explosive violence. Moreover, fluorination often involves extensive rupture of carbon-carbon as well as carbon-hydrogen bonds. The reaction can be made less vigorous by diluting fluorine with an inert gas such as nitrogen or argon. It is obvious, therefore, that the order of reactivity of hydrogen towards alkane is fluorine, then chlorine, then bromine, then iodine. Halogenation of higher alkanes. Formation of isomeric halogen derivatives. The halogenation of higher alkanes yields a mixture of all possible isomeric halogen derivatives. For example, the chlorination of propane gives a mixture of 1 chloropropane and 2 chloropropane. Further chlorination gives a mixture of 4 distribution products as 1,1-dichloropropane, 1,2-dichloropropane, 1,3-dichloropropane or 2,2-dichloropropane. The mechanism of halogenation is discussed a little later. Note, it may be seen that the halogenation of alkanes is an oxidative process because it involves replacement of electropositive hydrogen atoms by electronegative halogen atoms and is accompanied by an increase in the oxidation state of carbon. Nitration. This reaction involves the substitution of hydrogen atom of an alkane by nitro group, and it is carried out by heating the hydrocarbon in the vapor state with nitric acid at 700 Kelvin. During nitration, the rupture of carbon-carbon bond is some of the molecule also takes place. As a result, the reaction furnishes a mixture of different products. For example, the nitration of propane results in the formation of a mixture of 4 nitro compounds, which are 1 nitropropane, 2 nitropropane, nitroethane, and nitromethane. Sulfonation. It is a reaction involving the replacement of a hydrogen atom of an alkane by sulfonic acid group. Only higher alkanes undergo sulfonation by reacting with fuming sulfuric acid. For example, hexane on reaction with H2SO4 in the presence of SO3 gives hexane sulfonic acid plus H2O. Nitration and sulfonation are believed to take place by free radical mechanism. Oxidation. First is combustion. When burnt in excess of air or oxygen, alkanes undergo complete oxidation to produce carbon dioxide, water, and large quantity of heat. In spite of being highly exothermic reaction, combustion requires a high temperature, that of a flame, to start it. This is due to the energy of activation required to initiate the reaction. Due to the large quantity of heat produced during combustion of alkanes, this reaction has tremendous practical importance. Vast quantities of hydrocarbon obtained from the petroleum are used as fuels for the production of heat and power of combustion. The cooking gas, commonly known as LPG, the liquefied petroleum gas, is a mixture of propane and butanes compressed as liquid. Incomplete combustion of alkanes due to insufficient supply of air or oxygen results in the formation of a soot or a carbon black. This is used in the manufacture of Indian ink, printer's ink, black varnish, and as a filler or rubbers. Catalytic oxidation. When heated in a regulator supplied of air or oxygen at higher pressure and in the presence of suitable metallic catalysts, lower alkanes are oxidized to alcohol and aldehyde, while higher homologous yield long chain fatty acids. For example, when a mixture of methane and oxygen in suitable proportion is compressed to 100 atmospheres and passed through copper tube at 475 Kelvin, methane is oxidized to methanol. When a mixture of methane and oxygen is passed through heated molybdenum oxide, methane is oxidized to formaldehyde. Normally, alkanes resist the reaction of oxidizing agents such as potassium permanganate, but alkanes containing tertiary hydrogen atoms can be oxidized by such reagents to corresponding alcohols. For example, isobutane plus oxygen in the presence of alkaline KMnO4 give rise to tertiary butyl alcohol. Thermal decomposition or pyrolysis. This process involves the decomposition of bigger molecules into a small number of simple molecules by the action of heat. When heated up to 775 to 175 Kelvin, higher alkanes undergo pyrolysis to yield smaller and molecules. For example, propane decomposes follows at about 735 Kelvin. Propane gives ethylene plus methane 55% or propylene plus hydrogen 45%. It is apparent that pyrolysis involves the decomposition of carbon-carbon as well carbon-hydrogen bonds. The composition of products depends upon the nature of starting compounds and condition employed. The pyrolysis or thermal decomposition of alkanes obtained from the petroleum is commonly referred to as cracking or fragmentation. Cracking is a very important process from commercial point of view and is discussed in detail under petroleum. Aromatization. This process concerns the conversion of aliphatic hydrocarbons into aromatic hydrocarbons in the presence of suitable catalyst. The reaction involves dehydrogenation, cyclization, and even isomerization in some cases. It is generally carried out at high temperature of about 720 to 820 Kelvin, high pressure at about 10 to 20 atmospheres, and in the presence of catalyst. The reaction involves dehydrogenation, cyclization, and even isomerization in some cases. Thus, N-hexane changes into benzene and N-heptane changes into toluene. N-hexane at 770 Kelvin 10 to 20 atmosphere in the presence of Cr2O3 or Al2O3 gives benzene plus 4H2. N-heptane at 770 Kelvin 10 to 20 atmospheric pressure Cr2O3 and Al2O3 give rise to toluene plus 4H2. These days, the reaction is generally carried out at 670 Kelvin in the presence of platinum as a catalyst. Therefore, the reaction is sometimes termed as platforming. Seventh one is the isomerization, and it is the process of converting one isomer to the another. It is found that when N-alkanes are heated in the presence of aluminum chloride and hydrogen chloride, they are converted into branched chain isomers. Mechanism of halogenation of alkanes. Mechanism of halogenation. The halogenation of alkanes is known to be a free radical chain reaction. This is because it proceeds through a series of steps involving free radicals, each step generating a free radical that brings about the next step till the chain of these steps is finally broken. There are three fundamental stages of the chain reaction, namely the chain initiating step, the chain propagating step, and third one is the chain terminating step. Let us discuss the mechanism of halogenation by considering the chlorination of methane. First one, the chain initiating step. The reaction is initiated by the homolytic cleavage of a chlorine molecule into two chlorine atoms or free radicals, each carrying an odd or unpaired electron. The energy required for this is supplied by heat or light. The second one is the chain propagating step. Once the chlorine atom or free radicals are formed, each of them reacts with the methane molecule forming HCl and generating methyl free radical as shown in step 2. Each of the methyl radicals in turn reacts with another chlorine molecule to form methyl chloride. At the same time generate another chlorine atom or free radical as shown in the step 3, and this newly formed chlorine atom can react with another molecule of methane as shown in the free radical can again repeat the step 3 and so on. Thus the step 2 and 3 are repeated several times and the chain gets propagated till it is ultimately terminated. The chlorine atom formed in step 3 can also react with the methyl chloride formed to yield hydrochloric acid and a new substituted methyl radical as shown in the step 4. The substituted methyl radical would react with another molecule of chlorine to form dihalogenated methane as indicated in step 5. Theoretically, this process may extend further till all the replaceable hydrogen atoms in the methane molecule have been substituted by chlorine. The third one is the chain terminating step. The chain of reactions initiated and propagated as outlined above may be terminated if the free radicals combine among themselves without giving rise to any new radical as shown. The chances of free radical combining among themselves are very low indeed because of the very small relative concentration of free radicals in the reaction mixture. Still, such a combination cannot be completely ruled out. As this happens, the chain of steps initiated by the cleavage of particular chlorine molecules comes to an end, but other similar chains initiated by the other chlorine molecules continue to operate, and therefore the overall reactions keeps on progressing. Evidence in support of the above mechanism. The free radical mechanism of halogenation is supported by the following facts. First one is the reaction does not take place in the dark or at ordinary temperature but requires energy in the form of heat or light to initiate the process. This is because the reaction initiating step involves the dissociation of a halogen molecule into free radicals which require the supply of energy. The second one is the high quantum yield. For each photon of energy absorbed, many thousand molecules of alkyl halide are formed. This is evidently due to the repeating chain propagating steps. It has been observed that addition of substances that are sources of free radicals can initiate the reaction in the dark at temperature below 525 Kelvin, for example, in the presence of 0.02% of tetraethyl lead. Chlorination of methane proceeds in the dark at 415 Kelvin. It is also known that at 450 Kelvin, tetraethyl lead decomposes to give metallic lead and ethyl free radicals. It appears quite reasonable that the ethyl radicals formed in this manner attack chlorine molecules to produce chlorine atoms or free radicals. Reactivity and selectivity. Chlorination versus bromination. It has been studied earlier that in the halogenation reaction of alkanes, chlorine is more reactive than bromine. It has been discussed that in the case of alkanes containing different type of hydrogen atoms, the ease of abstraction or reactivity of different type of halogen follows the order tertiary, then secondary, then primary, irrespective of the nature of halogen taking part in the reaction. But now we consider a very interesting observation with the help of a simple example. When propane is subjected to chlorination, N-propyl chloride and isopropyl chloride are formed in the ratio 45:55. But when propane undergoes bromination, N-propyl bromide and isopropyl bromide are formed in the ratio 4:96. Keeping in view the number of primary and the secondary hydrogens, it is clear that the secondary hydrogens of propane are more reactive than the primary hydrogens in both the cases. But there is much more selective abstraction of secondary hydrogens in bromination than in chlorination. In general, the relative rate of abstraction of tertiary, secondary, and primary hydrogens of alkanes in chlorination at room temperature are 5 ratio 3.8 ratio 1, while in primary hydrogen of alkanes in chlorination is 5 ratio 3.8 ratio 1, while in bromination at 400 Kelvin the relative rates are 1600 ratio 82 ratio 1. This means that bromine is less reactive but more selective in its reaction with the different type of halogens. On the other hand, chlorine is more reactive but less selective. This is in accordance with the reactivity selectivity principle, according to which if the attacking species is more reactive, it will be less selective, which a less reactive species is more selective. In other words, bromine atom will attack the tertiary hydrogen relative much more easily than the secondary, which in turn would be attacked more easily than primary hydrogen. Hence, as compared with the more reactive chlorine, there will be much more selective in the reaction with less reactive bromine. Interconversion of alkanes. During the study of organic chemistry, we are often required to prepare one organic compound from another. Sometimes this may involve preparation of a higher member of a class of compound from a lower member, stepping up a series, or vice versa, stepping down the series. We will illustrate the procedure followed by considering the interconversion of alkanes. Preparing a higher alkane from a lower member, this involves two steps. First is the chlorination or the bromination of the given alkane into the monochloro derivatives. Second one is the Fuchs reaction or Core-House reaction of the monochloro derivative obtained with the suitable alkyl halide or lithium alkyl copper as required. And this is how we have finished our chapter alkenes. Thank you.